Usually when we look at a massive modern skyscraper,
Yeah.
we're mostly just marveling at the aesthetics, right?
Right, yeah, like the gleaming glass exterior or the high-speed elevators.
Exactly. The panoramic penthouse views.
You're interacting with the user experience, basically.
Yeah.
I mean, the carpet, the smart lighting, the paint on the walls.
But underneath all of that, holding thousands of tons of glass and steel steady against the wind is the concrete and steel foundation.
Yep.
And you might never actually look at it. You probably never even think about it.
Most people definitely don't.
Right. But the entire towering structure rests completely upon it. If that foundation is flawed, nothing else matters.
It's the invisible architecture that makes the visible world possible.
Okay, let's unpack this. We're looking at the ultimate digital foundation today on this deep dive. We're talking about the C programming language.
Oh, absolutely.
Because it was created over 50 years ago, and yet it remains the absolute undisputed bedrock of modern computing.
It really is.
So our mission today is to demystify why that is. And to help us do that, we're pulling from a fantastic book. It's called The C Programming Language, a comprehensive structural guide.
An absolute classic text.
Yeah, and we've also been analyzing this massive, highly detailed visual infographic. It maps out C's entire architecture.
Which was actually built entirely using open source tools, right?
Yeah, like pop.os, GNU Linux, GIMP, and Shotcut. It gave us this literal map of how the language operates.
What's fascinating here is the core tension of C itself.
Uh-huh.
I mean, its enduring power really comes down to a very unique, incredibly precise balance.
How do you mean?
Well, on one hand, it offers high-level structural programming, human logic, code that you and I can actually read, write, and conceptualize.
Right, looks like math and English mixed together.
Exactly. But on the other hand, it provides low-level hardware access, like complete machine control.
Oh, wow.
Yeah, it is extremely rare for a language to speak to both the human mind and the physical processor so effectively.
So to understand how it actually manages that balancing act, we kind of need to rewind to why it was born in the first place.
Back to the early 1970s.
Right. Inside Bell Labs.
A true hub of computer science innovation.
And at the center of it is Dennis Ritchie. He created C by evolving an earlier, simpler programming language that was known just as B.
Naturally, B comes before C.
Right, but Ritchie didn't invent C just to, see if he could. It was built out of sheer desperate necessity to write the UNIX operating system.
Right, because before C came along, operating systems were heavily reliant on assembly language.
And assembly is pretty bad.
Oh, assembly is incredibly tedious.
Mm-hmm.
You aren't writing abstract logic. You are essentially feeding instructions to the computer's processor, one microscopic hardware tick at a time.
Yikes.
And whereas assembly language is entirely tied to specific hardware. So if you spent years writing an operating system for one type of machine...
Wait, and then a new processor hit the mark?
You couldn't just port it over. You had to rewrite almost everything from scratch.
That sounds like an absolute nightmare for developers.
It really was.
So C comes along and provides this revolutionary middle ground. It's high level enough to let a developer structure complex logic easily, but low level enough to touch the memory directly.
Exactly. It made UNIX portable.
Suddenly, you could take this operating system and compile it across entirely different computer architectures.
And that portability became so vital that by 1989, the American National Standards Institute, ANSI, had to step in and formally standardize C.
Right, ANSIC.
Yeah, because as the language exploded in popularity throughout the 80s, different compiler manufacturers were introducing their own slight variations.
Which I assume broke things.
Yeah, it was leading to fragmented code. So
Okay.
standardization ensured that a well-written C program could run seamlessly on virtually any machine, effectively future-proofing the language.
Wait, let me push back on this history for a second.
Okay, sure.
If C was just built as a quick fix to port UNIX back in the 1970s, why didn't the tech industry just replace it when better, shinier technology came along in the 90s or 2000s?
That's a fair question.
Is it survival just legacy inertia? We just built too much on top of it and nobody wants to bother rewriting the foundation?
It is definitely not just inertia. Ritchie's design was fundamentally brilliant. C wasn't a quick fix. It was a foundational breakthrough in how humans communicate with processors.
Oh, really?
Yeah, because it allowed code to be compiled and run seamlessly across entirely different hardware architectures without losing that raw, bare metal performance speed.
Right. It stayed super fast.
Exactly. So it became the obvious choice for building the core of other technologies.
So it literally became the foundation for the skyscraper.
Yes. I think it's crucial for you listening right now to realize that almost every single device you use, including whatever you're using to listen to this very audio right now, relies on operating systems heavily rooted in Ritchie's breakthrough.
That's wild to think about.
Yeah, Windows, Mac, Linux, Android, the kernels of all these systems speak C.
Okay, so now that we know why it survived, let's get into how it actually speaks. How does C translate our human ideas into something physical memory can actually process?
Well, it starts with a very strict grammar.
A language with unforgiving rules.
Absolutely. Every C program is built around functions, and execution always begins at a specific entry point called the main function. But the most iconic structural rule of C is definitely the semicolon.
Oh man, the dreaded semicolon.
Yes.
Hmm.
In C, a semicolon acts as a hard full stop for instructions.
It tells the compiler, this specific thought is finished. Physically prepare the processor for the next one.
Exactly.
And to build those thoughts, developers use keywords, which are, built-in vocabulary with special commands, and identifiers, which are the custom names you give to your own variables.
Right. But we need to unpack how it handles data, because this is where C really forces you to think like a computer.
Yeah, because in modern languages, you just type a number and the computer figures it out. But in C, you have to use primitive data types.
Yeah, you have to explicitly declare what kind of data you are creating, like int for whole numbers, char for single characters.
Float for fractional decimals, right?
Yeah, and double if you need extremely high precision decimals.
But why, though? Why can't the compiler just look at the number 5 and know it's a number?
Because C touches bare metal. It forces you to declare if a number is a whole int or a decimal float, so the compiler knows exactly how many physical bytes of RAM it needs to reserve.
Oh, I see.
An int might take 4 bytes, a double might take 8 bytes. When you are managing limited memory, every single byte matters.
That makes total sense. And there's also void, right? Which literally represents the absence of a value.
Yeah, void.
It seems weird to have a data type for nothing, but the guide says it's incredibly useful when a function needs to perform a physical action on the screen, but doesn't actually need to hand a mathematical result back to the system.
Exactly. It's all about strict memory management.
Which brings us to how C handles the lifespan of this data. We're talking about storage classes, which dictate how long data actually lives in the computer's memory before it gets wiped.
Right.
And looking at the architecture map for this, I immediately pictured Office Dynamics.
Office Dynamics. Okay, I want to hear this.
Hear me out. So you have the auto storage class, that's the default. A variable is created when a function starts, and it is entirely destroyed the moment the function finishes.
Okay.
That's your temporary worker. They come in for a specific task, they do it, and they leave immediately, freeing up disk space.
Ah, highly efficient use of RAM. Okay, I like it.
Right. Then you have the static storage class. This is the veteran employee who never forgets what happened yesterday.
Right, because even after the function finishes running, a static variable quietly retains its final value in memory.
Exactly. Waiting patiently for the next time the function is called. It remembers past states without needing to be recreated.
Makes sense.
Then you have extern, which allows variables to be shared across completely different files, like a company-wide memo on a bulletin board.
Nice.
But my absolute favorite is the register storage class.
Ah, the register keyword. That is a fascinating piece of C's design.
In my office analogy, the register variable is the executive assistant who gets to sit right inside the CEO's office.
The CEO being the central processing unit.
Exactly. They bypass the regular office cubicles, the standard RAM for lightning-fast access.
I love that analogy. And if we connect this to the bigger picture, the register keyword highlights a brilliant hardware limitation.
Really?
Yeah, you can use register to politely request that the compiler put your variable directly into the CPU's internal register for maximum speed, bypassing RAM entirely.
But it is only a request, right?
Exactly. It's just a request.
Wait, the compiler can just say no.
Oh, absolutely.
Yeah.
If the CPU is already too busy, the compiler will ignore your request and put the variable in standard memory anyway. CPU registers are incredibly fast, but physical space on the chip is highly limited. C gives you the ability to ask for extreme performance, but the hardware always has the final say.
Man. Well, storing data and setting its lifespan is only half the battle.
Right.
To make software actually do something, we have to manipulate that data. C gives you standard operators, addition, subtraction, true-false relational comparisons. But the real power lies in bitwise operators.
Oh, yeah. Bitwise operators give C its reputation for ultimate control.
This blew my mind. We're talking about manipulating data at the most fundamental binary level, the actual ones and zeros.
Most programmers today just use the standard arithmetic operators,
Mm.
but bitwise operators let you shift binary digits to the left or right.
Which sounds neat, but what does it actually do?
It's not just a neat trick. Shifting a binary number one position to the left literally multiplies that number by 2 at the physical hardware level.
Bypassing the processor's arithmetic logic unit entirely.
Precisely. It is infinitely faster. You wouldn't use this to write, like, a simple web app, but if you were writing systems programming or device drivers, and you need to squeeze maximum performance out of limited hardware.
Bitwise operators are absolutely crucial.
Exactly.
It's like reaching past the steering wheel and manually turning the gears in the engine with your bare hands.
That's a great way to put it.
And to manage all these operations, C uses control flow statements, loops, and conditionals. But I want to zero in on what are called jump statements, specifically the goto statement.
Ah, the infamous goto.
Right. The guide explicitly notes that goto is generally discouraged by modern developers
Very discouraged.
because it allows you to abruptly leap directly to any labeled point in your function. But if jumping randomly around the code is considered a terrible habit that turns your program into an unreadable mess, why does the compiler still allow it?
Well, this is a perfect example of the raw, unapologetic power of C. You see, in modern high-level languages, goto is often completely removed from the syntax to protect programmers from themselves.
Right.
C doesn't police your choices,
It just hands you the chainsaw and trusts you not to cut your arm off.
basically. Because occasionally, in highly complex systems programming, you might find yourself trapped in a deeply nested set of hardware checks.
Okay.
If a critical error occurs deep inside that nest, an emergency go-to leap is simply the most efficient, fastest escape hatch to jump out of the loops and handle the error. C trusts you to use dangerous tools responsibly.
But as you can imagine, if programs are using complex nested conditions and emergency jumps, the kind can quickly turn into chaos.
Oh, for sure.
So to prevent this, C forces programmers to modularize their code using functions.
Grouping logic into reusable blocks.
Yeah. The architecture map distinguishes between a function prototype and a definition.
Right.
The prototype is introduced at the very top of the file. It's just a blueprint telling the compiler, hey, this function exists, here is its name, and here is the exact data type it will return. Then, later on, you write the actual definition, which is the code itself. What I found really interesting is how you hand data over to these functions.
Ah, passing parameters by value versus passing by reference.
Exactly. Call by value creates a safe, completely independent copy of your data. The function can calculate things using the copy all it wants, and your original data stays safe in memory.
Safe and sound.
But call by reference passes the exact memory address to the function. The function reaches back and alters your original variable directly.
It's the difference between giving someone a photocopy of your recipe versus giving them your original handwritten family recipe card and letting them cross things out with a Sharpie.
That's terrifying. Why take the risk of handing over the original, though?
Efficiency. If your variable is a massive data set, creating a physical photocopy in the computer's RAM takes time and consumes memory.
Oh, I see.
Handing the function a lightweight reference to where the original data lives is incredibly fast.
That makes sense. And speaking of efficiency, functions can also use recursion, meaning a function is fully permitted to call itself.
Yes, it's an incredibly elegant way to solve complex problems that break down into smaller identical subproblems, like navigating a massive maze of computer folders.
But the non-negotiable rule of recursion is the base case.
Very important.
You have to program a specific condition that tells the function to finally stop calling itself. Otherwise, it creates an infinite loop, consumes all your memory, and crashes the system.
A literal death spiral for the program.
Right. And this idea of knowing when to stop connects perfectly to how C organizes larger sets of data, like arrays. Arrays group multiple elements of the exact same data type into a single, continuous block of memory.
Yeah, you can have 1D arrays, which are simple lists, or multidimensional arrays like 2D grids, almost like a spreadsheet for mapping pixels on a monitor.
Okay, here's where it gets really interesting. I was looking at how C handles text.
Ah,
Yeah. Unlike modern languages, C doesn't actually possess a dedicated built-in data type for words or sentences. It uses strings, which are just one-dimensional arrays filled with individual characters.
Yep.
And looking at the architecture, I realized C doesn't comprehend words at all. It's like lining up wooden alphabet blocks on a long table.
I like this.
If you don't place a blank block, the invisible null terminator, at the very end of your word, the computer will just keep reading right off the table.
It absolutely will.
It will literally just start reading random computer memory out loud.
That wooden block analogy captures the exact mechanism. Both recursion and C-strings require a strict stop sign, a base case for the function, and a null terminator for the string.
Right.
Without them, C doesn't have the built-in intuition to stop. It will blindly follow your instructions until it reads memory it shouldn't, or executes a loop too many times, and the operating system steps in and shuts the whole program down.
Which is terrifying. And that danger of reading past the end of a string brings us to the ultimate power and peril of C. We were talking about memory management.
Yes, the ability to bypass abstractions and dictate exactly how physical RAM is organized.
Right. But before we get to pointers, we have to talk about how C lets developers build their own custom data structures. We mentioned primitive types earlier, like int and char, but C lets you group these together using structs and unions.
A struct is essentially a custom container.
Like grouping related data.
Exactly. If you are coding a video game character, you don't want their health, their name, and their speed floating around as separate variables in memory.
Right, that would be messy.
So a struct lets you bundle an int, a char array, and a float into one single logical package in memory.
Makes perfect sense. But then there are unions. And reading about unions felt like reading about a magic trick that could easily go wrong.
They are tricky.
A union lets you bundle different data types together, just like a struct, but it forces them to share the exact same physical memory location.
Extreme optimization.
Right. So if you have an int and a float in a union, they're literally overlapping in the same 4 bytes of RAM. If you change the int, you instantly overwrite the float. You can only safely use one at a time.
Yep.
Why would anyone want overlapping data?
Imagine writing software for a tiny embedded sensor on a spacecraft where you only have kilobytes of total memory available.
Yeah.
You can't afford to waste space on variables that aren't being used simultaneously. Unions let you aggressively recycle the same physical memory space for different purposes.
It's brilliant, but incredibly risky.
Very risky.
And that risk is magnified 100 times by the absolute pinnacle of C programming, which is pointers.
Pointers are what separate C from almost everything else.
Right. Because instead of holding actual data, like the number 5, a pointer is a variable that holds the literal hexadecimal memory address of another variable. It's like, instead of the computer wasting time and effort physically copying an entire house to hand to a function, you just hand the function a piece of paper with the GPS coordinates of the house.
It's infinitely faster.
It is, but if you write down the wrong coordinates on that piece of paper, the function drives to the wrong location and bulldozes the wrong neighborhood.
And when you couple pointers with C's dynamic memory allocation tools, functions like malloc, to actively request chunks of RAM on the fly and free to release it back to the system,
Right.
you give the programmer absolute unmitigated control over the hardware. You aren't just writing software. You're actively managing the physical chips inside the machine.
Okay, but doesn't giving flawed humans direct control over physical memory addresses sound like a recipe for absolute disaster? What if you forget to use that free command and give the memory back?
This raises an important question, and honestly, the blunt answer is yes. It often is a disaster.
I knew it.
If you point to the wrong memory address, you overwrite data you shouldn't. This is the root cause of massive security vulnerabilities or catastrophic system crashes.
And if you forget to free the memory...
Yeah. If you forget to free memory, you create a memory leak. Your program silently hoards memory until it eventually consumes all the computer's resources. This is exactly why C is both revered and feared.
And the language absolutely refuses to hold your hand when these things go wrong. Modern languages have these nice, safe try-catch blocks that gently catch exceptions and keep the program running.
Not C.
Nope, C does not.
C relies on a global integer variable called erno, the error number. If a critical system function fails, it doesn't gracefully pause, it returns a negative flag, and then you manually have to check the erno variable to see what numeric code the system generated.
And nobody wants to memorize hundreds of numeric codes.
Definitely not.
Fortunately, C provides 2 essential functions to help. Pairer, which automatically translates that error number into a human-readable message and prints it right to the screen.
Very handy.
And strer, which takes the error number and returns a direct pointer to the official text description. That allows you to seamlessly log the error quietly in a background file without forcing an ugly error code onto the user's screen.
Which proves exactly who this language was designed for. C's error handling wasn't built for beginners who want a safety net. It was built for engineers who want absolute transparency about exactly what failed at the bare metal level.
So what does this all mean? We've journeyed from Dennis Ritchie's desk at Bell Labs in the 70s, all the way down into the granular hardware control of bitwise operators.
It's a huge span of control.
We've looked at the strict discipline of storage classes, the perilous overlap of unions, the massive power of pointers, and the extreme optimization of manually allocating memory.
We've seen how C forces the developer to understand not just the abstract logic of their program, but the physical, electrical reality of the computer running it.
Exactly. C remains the undisputed bridge between human ideas and a raw computing hardware. And I want you, the listener, to keep this in mind. The next time your phone seamlessly switches between apps, or your laptop instantly loads a massive file, or your smartwatch tracks your heart rate,
Think about that invisible architecture.
think about C running silently underneath it all, managing the hardware byte by byte, memory address by memory address, holding the entire skyscraper steady.
I'd like to leave you with one final thought, actually. Something essential to consider about the evolution of code.
Oh, definitely.
If C's unparalleled power comes from the fact that it intimately trusts the programmer with direct, unshielded hardware access, what happens to the future of technology as we increasingly rely on modern, high-level languages?
That's a great point.
Languages that intentionally hide the physical hardware from us behind layers of safety nets and automatic memory management. By abstracting away the machine, by ignoring the concrete foundation to only focus on the glass and the paint, are we slowly losing our fundamental understanding of how our own computers actually work?
Something to ponder next time you ride the elevator to the penthouse. Thanks for joining us on this deep dive.